Now, we can extend the previous theorem, the one that stated that the Laplace transform of the derivative of a function, so this is another way of writing f prime of t, is equal to s times L of f of t minus f of 0. We can extend that to higher order derivatives using induction, and we get the following theorem. So let f of t, f prime of t, up to f, the n minus first derivative of f at t, be continuous on the left closed interval 0 to infinity, and let the nth derivative of f be piecewise continuous on the left closed interval from 0 to infinity, with all of these functions being of exponential order alpha. Then for s greater than alpha, the Laplace transform of the nth derivative of f is given by s to the power n times the Laplace transform of f minus s to the power n minus 1 times f of 0 minus s to the power n minus 2 times f prime of 0 minus dot 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 minus the n minus first derivative of f evaluated at 0. So what I will do here is I will prove this theorem for just the case n equals 2, and then I hope that you see how you can extend that to n equals 3, 4, etc. So this is only for n equals 2. So what we're going to do is we're going to take the Laplace transform of f double prime of t. And we're going to see what that is. So I'm going to write that as follows. I'm going to write that as the Laplace transform of the derivative of the derivative. Right? The second derivative is the derivative of the derivative. But by theorem 4 from the previous video, we can write this as s times the Laplace transform of not f of t here, but f prime of t. So this is f prime of t. And then we have to not subtract f of 0 because we used f prime here. So we're going to subtract f prime of 0. So now here comes the induction part. We can now rewrite this part, the Laplace transform of f prime, again using that original theorem. So this will be equal to s times the Laplace transform of the derivative of f of t, and then we're still subtracting f prime of 0. And so if we use this theorem again, we get s times, and then s times the Laplace transform of f of t, and then minus f of 0. So that's just rewriting this part, and then we still have minus f prime of 0. And so for the second derivative, we get s squared times the Laplace transform of f of t evaluated at S, and then minus S times f of 0, and then minus f prime of 0. And you should verify that this part is the same as here with n equals 2. So we have that s squared, then s to the power 2 minus 1 is just s times f0, and then the n minus first derivative is f prime of 0. So that is the proof for the case n equals 2. And then we can go farther by saying the f triple prime is the derivative of f double prime. And so you can get as high as you want in terms of the degree. So let's do an example with that. So find the Laplace transform of f of t equals cosine b times t using theorem 4 and the fact that the Laplace transform of sine of b of t of s is equal to b over s squared plus b squared. So what we're going to do here is I'm going to let f of t be equal to sine b of t. So then I know that f of 0 equals 0, no matter what b is, because when I plug in 0, I get sine of 0. And I also know that f prime of t is equal to b cosine of bt. By the chain rule, I have to multiply by b. So now let's take a look at what is the Laplace transform of f prime of t. Well, by theorem 4, this is s times the Laplace transform of f of t minus f of 0. So this is theorem 4 from the previous page in your notes and the previous video. So let's plug in what we know. The Laplace transform of f prime of t, which is the Laplace transform of b cosine bt, is equal to s times the Laplace transform of f of t. So that's the Laplace transform of sine of b of t. And then minus f of 0. So that's minus 0. Now we can pull that constant b outside because of the linearity of the Laplace transform. And so that's the Laplace transform of cosine of b of t times s is s times the Laplace transform of sine bt is given over here. So that's b over s squared plus b squared. And then we're asked to find the Laplace transform of this. So what we can do is we're going to divide both sides by b. And what we're left with there is that the Laplace transform of cosine b of t is given by S over S squared plus B squared. Now, of course, you could also look this up in a table, and so this does not make for a good exam problem here, but it shows the strength of that theorem that we can find one Laplace transform from another by just some manipulation here, and we don't have to do an improper integral. Now, one other question that we can ask ourselves is that if capital F of S is the Laplace transform of some function f of t, is the derivative of capital F with respect to S also the Laplace transform of some function of t? And the answer is yes. We can actually show that capital F prime of S is the Laplace transform of negative t times f of t evaluated at S. And in general, the following holds for higher order derivatives. So if capital F of S is the Laplace transform of some function f, and we assume that f of t is piecewise continuous on the left closed interval from 0 to infinity and of exponential order alpha, then for s greater than alpha, the Laplace transform of t to the power n times f of t is equal to negative 1 to the power n times the nth derivative of capital F of S. And we'll do an example in the next video that shows how to use that.